Okay, so in this lecture we'll discuss in brief about sampling theorem. You already have a good idea about the sampling theorem as you've done it in your signals and systems course already. So as we know that sampling theorem, it is one of the most important theorem in the analysis of the signals, and it has huge applications in signal processing and communications. So sampling is one of the basic step or the process that is involved in almost all the signal processing and communications. Okay, so the all the latest signal processing and you can say digital communication methods, they are based on the validity of this theorem, sampling theorem. All the, you can say, all the latest signal processing and digital communication concepts are based on the validity of sampling theorem. It's a very important theorem from the prospects of the communication domain, right? So the idea behind proper sampling of a signal is quite simple. If we have a continuous time signal, let's say if we have a continuous time signal, we take the samples of the signals, instantaneous value of that signal at fixed intervals. Okay, so this is the idea of sampling, but this sampling process has to be proper. The sampling frequency fixed has to follow certain norms that is defined by sampling theorem, so as that means the methods followed by the sampling and subsequently at the receiver and the detection of the signal, those are not disturbed. So the sampling theorem plays a very important role in this. Sampling theorem says that a continuous time signal, a continuous time signal can be sampled and recovered back from the knowledge of the samples only if the sampling frequency fs is greater than equal to twice of fm, where fm is the maximum frequency present in the message signal, maximum frequency component. So if this rule is being followed while sampling a signal, then we can say that it obeys the sampling theorem, and it can be sampled as well as recovered back from the knowledge of the sample. The signal at the receiver end can be reconstructed back once we have the knowledge of the samples, but this rule has to be followed. This is the sampling theorem. Just for an example, if we take different signals, let's say if we take a DC signal, it's a DC signal having zero frequency, it is continuous in nature, right? And if we take multiple samples at fixed intervals, right, subsequently we take another signal that is a sinusoidal signal, and again we sample this signal at fixed interval, and so on. And again we take a signal and we take sampling frequency as this. Alright, so in this case, the first case, we know that it is an analog DC signal, and or it can be considered as a cosine waveform with zero frequency, right? And since analog signal is a series of straight line between each sample, so if we want to reconstruct the signal back at the receiver end, we can just join these sample points and we can easily reconstruct back our original analog DC signal, right? So it's really simple and desirable thing, right? So this could be regarded as a proper sampling scenario. Now moving on to the second case, let us say the maximum frequency, the frequency of this cosine signal is f, and the sampling frequency here is fs is equal to 11 times f. That means 11 samples have been taken in one time period. 11 samples have been considered in one time period, right? In one cycle, or you can say. Okay, so if we assume that the frequency f, the frequency of this waveform is 1 kilohertz. So the sampling frequency present over here is 11 kilohertz, isn't it? And now it can be seen that if we only analyze these samples, can we reconstruct back our original cosine waveform with the knowledge of these samples? Yes, we can do that. Just by joining the values of these samples, we can reconstruct back the original cosine signal waveform, since the sampling frequency is quite large. There are 11, that is 11 kilohertz, or we take more number of samples in 1 second. That is, if the sampling frequency is 11 kilohertz, what does that mean? We are taking 11,000 samples per second. So if we are taking these many samples per second, so obviously it will be quite convenient to reconstruct back the original signal at the receiver end. That is the concept. Now if we talk about the third case, let us say the frequency over here is suppose 3 kilohertz. Alright, and the sampling frequency considered over here, you can see there is only one sample in one cycle. Fs, the sampling frequency, is also equal to f, that is 3 kilohertz. You can clearly see there is only one sample per cycle. So now will this be a desirable scenario for the sampling and the reconstruction back of the signal? Clearly no. So since the samples, the number of samples are too less, it is only one sample in one cycle. Okay, one sample per cycle, right? So we can infer that from this figure that the reconstructed signal from the samples, it is very hard to match, to get this original signal by joining these two samples. We cannot predict the original signals just with the knowledge of one sample per cycle, isn't it? So it is very hard to reconstruct back the original signal that matches the reconstruct back the signal that matches the original signal, right? So this clearly does not follow the sampling theorem, and we know that because this fs, sampling frequency, is equal to f. So sampling theorem says that at least the sampling frequency should be twice of fm for proper reconstruction of the signal. And this term is known as Nyquist frequency. So while discussing the sampling theorem, two terms are widely used, which are Nyquist frequency and Nyquist rate. Okay, so Nyquist frequency is nothing but twice of the maximum frequency present in the signal. And Nyquist rate is nothing but it is the minimum sampling rate, which is equal to 1/2 of the sampling rate, right? It is the minimum sampling rate. Alright, so these two terms are widely used when we are discussing about the sampling in particular. Now let us analyze the situation. What happens when the sampling frequency is less than twice of FM. What happens in this scenario? We say that this contributes to aliasing error. Aliasing error. Now let us see what is this aliasing error. Let us try to understand this concept of aliasing error with the help of some plots. Let us assume that we have a continuous time signal xt. Any random signal, we assume it to be a random signal, right? And its corresponding frequency domain counterpart is something like this, x of omega. This is the time domain representation, and this is the frequency domain representation of it, omega m minus omega m. This is the maximum frequency present in this signal, right? So now when we sample this signal, that means we are multiplying it with an impulse train having a sampling frequency, right? That means we are multiplying the signal with a impulse train. By sampling, we are multiplying it with the impulse train. Okay. So when we are multiplying it with impulse train in frequency domain, it will be convolution of the frequency domain of both. So this is the frequency domain of this signal. Frequency domain of impulse is a what? We know that the frequency domain of impulse is again impulse, right? So, and multiplication in time domain results into convolution in frequency domain. So when we convolve these two, this spectrum with this impulses, the resultant would be something like this, 0 omega m minus omega m. And when we convolve this spectrum with this impulse, you will get a shifted spectrum, right? Shift by omega s, omega m, sorry, yeah, this would be now omega s plus omega m. This would be omega s minus omega m, and so on. There will be shifted spectrums at the harmonics of the sampling frequency, twice of omega s similarly on the negative part of the frequency. Now if you see that if omega s, this omega s is the sampling frequency, if omega s is greater than equal to twice of omega m, which is the desirable condition according to the sampling theorem, if omega s is greater than equal to twice of omega m, so clearly we can say that there would be a sufficient guard band between the two shifted spectrums, right? Because if this is omega s, so this is equal to omega m plus this region x, let's say x, and this, right? So this would be, so clearly you can see it from the simple mathematics. This is omega m, this is also omega m, this is x, so omega m plus x plus omega m is equal to omega s here in this case, right? So if omega s is greater than twice of omega m, so this x will have some positive value and there will be a sufficient guard band between the two spectrum and there is no distortion in the signal. On the other hand, for the case when omega s is less than equal to twice of omega m, or less than twice of omega m, in that case what will happen? This x will be negative, right? So there is no sufficient guard band between the two shifted spectrums and these will overlap. So if this is 0, this is omega m, this is omega s, this is omega s minus omega m, clearly there is some overlapping between the adjacent spectra, right? And thus leading to distortion. And it becomes impossible at the receiver end to retrieve back the original signal. This kind of error is known as aliasing error, and it occurs when the violation of sampling theorem takes place, that is omega, the sampling frequency is less than twice of fm. Next we'll look at the pulse amplitude modulation. And you'll find that there is a high correlation between the sampling process and the pulse amplitude modulation type of the modulation schemes. So the PAM, which is the pulse amplitude modulation, it is the simplest form of pulse modulation. You can say it is the simplest form of pulse modulation. There are several different types of pulse modulation that we've already discussed in the previous lecture. So in this particular type of modulation, that is the PAM modulation, the signal is sampled at regular intervals and each sample is made proportional to the amplitude of the signal at the instant of sampling. So it's very simple to define PAM. In PAM, the signal is sampled at regular interval intervals and each sample is made proportional to amplitude of signal at the instant of sampling. That is, if we have, let us say, a continuous time signal, a sinusoidal continuous time signal, its corresponding PAM signal would be something like this. So it would be corresponding PAM signal in double polarity. This is your double polarity PAM, and similarly we can have a single polarity corresponding PAM, that would be this will be your single polarity PAM. There's only a slight difference between these two, double polarity and the single polarity PAM. In case of a single polarity PAM, we can say a fixed DC level is added to the signal. A fixed DC level is added to this double polarity PAM to ensure that all the pulses are positive. That is the only difference between the single polarity and the double polarity type of the PAM signal. Okay, next if we look at the natural sampling process, and it is exactly same as that of the PAM, you will see. So in PAM modulation, we know that the amplitude of pulses are varied in accordance to the modulating signal, correct? You can clearly see if this is the modulating signal or the message signal, the amplitude of the pulses are varied in accordance to the, if we look at the amplitude of these pulses, these are varied in accordance to the modulating signal. So in case of natural sampling, let's say modulating signal is empty, your message signal, and pulse amplitude modulation is achieved by multiplying carrier pulse train let us represented by VPT to this message signal. Okay, just by multiplying these two, we can achieve this PAM modulation, right? So we use a balanced modulator for the multiplication process. We multiply MT with the pulse train to get our PAM signal. This is your PAM generator, and this is your balanced modulator. This is nothing but your balanced modulator. We know the circuitry of balanced modulator as well, we have done it previously, right? So it is nothing but a multiplier. the output is a series of pulses. You can clearly see the output is a series of pulses, and the amplitude of which vary in proportion to the modulating signal. That is the concept of PAM, right? This type of PAM modulation is called natural PAM, since the top of the pulses is not flat in this case. That is, if we are talking about such a sinusoidal signal, and if we multiply it with the train of pulses, right, the resultant expected is something like this. Okay, so clearly you can see that top of the pulses, it is not flat, but it takes the natural shape of the message signal. Hence it is called the natural PAM. PAM, or natural, we also call it as natural sampling. Okay, because it follows, the top follows the shape of the modulating signal. Top follows the shape of modulating signal, right? So if we represent the pulse stream in Fourier series, because it's a periodic signal, so Fourier series representation of pulse stream, it would be something like this: a naught plus summation n is equal to 1 to infinity an cos 2 pi nt by ts. Okay, where ts is the time period of the pulse stream, and it can be simplified as a naught plus a1 cos 2 pi t by ts plus a2 cos 4 pi t by ts, and so on, right? So if you multiply this is your pulse stream. For the series representation of the pulse stream, if you multiply this pulse stream with the message signal, that results into your PAM. If you multiply it with the pulse stream, so this mt into vpt, so this becomes a naught into mt plus a1 into mt cos 2 pi t by ts plus a2 cos 4 pi t by ts, and so on, a2 mt, right, and so on, right? So if we assume that the spectrum of the message signal is something like this, let's say something like this, spreading from 0 to w, amplitude is aw, and so this is the spectrum of the message signal. So the corresponding spectrum of the modulated PAM signal, what would be the spectrum of the PAM signal? This message signal is multiplied with constant values a naught, and there are other terms as well. So this a1 into mt, but it is also multiplied by cosine term. Cosine terms, if we look at the Fourier transform of the cosine term, it is impulse in nature, so it will be shifted spectrum, right? The spectrum would be something like this: 0 to w, and this amplitude will be a naught times aw, right? And second would be at shifted at fs, so this will be a1 times aw, right? And similarly the third will be at twice of fs, and so on. Alright, so this is the spectrum of the PAM signal, which is corresponding to the spectrum of this message signal, right? So this is the natural PAM, you can say, because the top of the modulated waveform is in the shape of the modulating signal. Alright, Alright, so we'll move on to the other types of the sampling, that is flat top sampling and the other pulse modulation techniques in the next lecture. Thank you.